Okay, let's look at the section 5.4 continued. All right, so here's an example. Let f of x is equal to x to the fifth plus 2x minus 5. Right? Then there exists a unique, so this is a symbol for unique. Okay, so which means there's only one x value between negative 1 and a positive 2 such that f of x equal to 0. So it just means that there's going to be an x-intercept between 1 and 2, and there's only one of them, right? Right, so in order to prove this, we have to borrow a theorem from calculus called the intermediate value theorem, which states that if function is continuous on a closed interval from a to b, and k is any number between f of a and f of b, then there exists some number c between a and b such that f of c is equal to k. Right? So in this case, in order to apply this, our a value is 1, right? Then b is 2, because interval is from 1 to 2. And the k is going to be 0. So that's going to be 0, right? Right, so let's make sure that this function satisfies the hypotheses of this intermediate value theorem. Right, so 1. Right, we know that f is continuous. In fact, it's continuous everywhere, but we just want it's continuous on interval from 1 to 2. Right. Justification for that is since f is a polynomial function, so I would just say polynomial. Right? And 2. Right? We have to verify that 0 is between f of 1 and f of 2. So let's compute f of 1. So f of 1 is equal to, right, plug in 1, so it's going to be 1 to the 5th power plus 2 times 1 minus 5, right, which is going to be 1 plus 2 is 3 minus 5 is negative 2, right? This is simply just doing algebra, right? And 2, we have to, actually 3, we have to look at f of 2 as well, right? So it's going to be 2 to the 5th power plus 2 times 2 minus 5, right? So that's going to be equal to, right, 2 to the 5th power, so that's going to be 32. 32 plus 4, so 36 minus 5 is 31, right? This is just doing algebra, all right? All right, so from here, we know that the 0 is between negative 2 and 31, so we know that line 4, right? 0 is between f of 1 and f of 2, right? So this is just from line 2 and line 3, right? We have that. All right, so it satisfies both of these hypotheses. So f is continuous, right? Then 0 is between f of 1 and f of 2, so it satisfies that, right? Then we can apply the intermediate value theorem. So by intermediate value theorem, we can say that there exists some number x between 1 and 2 such that f of x is equal to 0, right? So this is by intermediate value theorem, right? That will establish the existence of such x, right? Now we have to prove that that's the only x we can find. So there's exactly one x value between 1 and 2 such that the f of x equal to 0, right? So this is actually proof by contradiction, right? So we know that there exists at least one, right? Let's assume that there are more than one, right? So assume 1. We assume that right, there exists, right, a couple numbers, say x1 and x2, which is between 1 and 2, right, such that, right, x has to be, so x1 and x2 are different, and at the same time, right, f of x1 and also f of x2 gives you 0, right? So this is just a given, right? A little space is tight, given. All right, then 2. Without loss of generality, we can also further assume that, okay, so x1 and x2 are different, distinct. So one has to be bigger than the other guy. So I'll just assume that x1 is the smaller guy and x2 is the larger guy, right? So this is simply without loss of generality, right? But if that's the case, we can just compare term by term. Then we can see that if you look at x1 to the 5th, right, x2 to the 5th, right, because this is between 1 and 2. So of course, if you raise the bigger number to the 5th power, it's larger than smaller number to the 5th power. And same way, if you compare 2x1 and 2x2, obviously 2x2 is larger than 2x1 because x2 is larger than x1. All right, then minus 5, subtracting 5 from both sides doesn't really change anything. So we have this inequality. Right hand side is definitely larger and the left hand side, right? So just this comes from line 2, right? But which means that 4, right, this is exactly the same thing as f of x1, and the right hand side is exactly the same thing as f of x2. So f of x2 is larger, strictly larger than f of x1, which is a contradiction because it contradicts line number 1, because f of x1 and f of x2 are both equal to 0, so they are the same number. So this contradicts line number 1, all right? Right, so therefore we have a contradiction, so which establishes that we cannot have more than one x value between 1 and 2 such that f of x equal to 0. Right, so that's it. Combining those two proofs, we could establish that there exists unique x value between 1 and 2 such that f of x equal to 0. Right, that's it. I hope that this was clear.